Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
So, I want you to picture this. It's early September 1859.
Right.
And telegraph operators all across North America and Europe too, actually, they start experiencing something completely inexplicable.
Yeah, it was basically a global technological meltdown, given what they had back then.
God, I mean, their machines are literally shocking them. Sparks are just leaping out of the equipment.
Right.
In some of these offices, the telegraph paper just spontaneously bursts into flames.
Which, is terrifying if you're just sitting at your desk.
Totally terrifying. And the craziest part is, these operators, they found that they could physically disconnect their batteries, like completely cut the power to the machines. And they could still send messages using whatever this phantom, energy was that was surging through the wires.
It's just wild to think about.
It is. And the culprit wasn't like a sudden surge in Earth or weather. It wasn't human error. The culprit was actually 93 million miles away.
Yeah, it was what we call the Carrington event today. And it was the result of this massive, just unimaginably huge magnetic storm that slammed straight into the Earth's atmosphere.
Wow.
I mean, at the time, human technology was basically just relatively simple wires strung up on wooden poles,
Right, yeah.
And it was still enough for this solar event to just completely overwhelm the entire system.
Which is just, it's deeply unsettling, because I want you to step outside on a perfectly clear, beautiful day, right? And just look up at the sky.
Obviously not directly at the sun, but yeah.
Right. Don't stare at the sun. But from our vantage point down here, the sun just looks like this calm, permanent, unchanging bright spot.
Yeah, it looks totally static.
Exactly. It's this reliable, glowing disk. It warms your skin. But the Carrington event kind of proves that this outward appearance is, it's perhaps the greatest illusion in the entire solar system.
Oh, absolutely. The disconnect between what our eyes actually perceive and what physics tells us is going on up there is staggering.
Because beneath that calm yellow glare, it's this roiling, violently dynamic celestial body. I mean, we are talking about a monster basically wrapped in twisting electrical currents and these incredibly tangled magnetic fields.
Yeah, and we build our whole lives around it, right? Our seasons, our daily routines, our agriculture. We build all of that around the assumption of its quiet, steady reliability.
Right.
But in reality, it is a highly charged, magnetically chaotic engine that is constantly at war with itself.
A chaotic engine. I love that description, because today, that is exactly what we are unpacking. We're looking at the hidden engine inside our star.
And there is a lot to unpack.
There really is. We're going to explore the sun's heartbeat, basically, this roughly 11-year cycle of building tension. We'll look at the periods of deceptive calm and then the periods of absolute chaotic eruption.
Yeah.
And we're going to understand exactly how this massive magnetic engine controls not just the space weather around our planet, but potentially like the existence of life across the entire universe.
It's a huge topic. But to understand any of this, we first have to kind of fundamentally shift our view of what the sun actually is.
Okay, how so?
Well, we have to stop thinking of it as a solid object. It's not a glowing rock.
Right.
And it's also not just a giant ball of gas like a balloon.
Okay, so if it's not a rock and it's not gas, what is it?
It is a massive electrically conductive fluid.
Okay, I need to pause you there for a second.
Oh.
Because when I think of a fluid, I immediately think of water, right?
Sure, yeah.
And when I think of a magnetic generator, I think of solid metals, like copper wires spinning around iron cores inside a power plant.
Right, a traditional dynamo.
Exactly. So how does a fluid made mostly of hydrogen, no less generate a massive magnetic field?
So the key here is the state of matter. The sun is composed almost entirely of plasma.
Plasma.
Right, which is often called the fourth state of matter. Basically, if you take a gas, say hydrogen or helium, which make up about 98% of the sun's mass, and you heat it up to millions of degrees, what thermal energy becomes so intense that the atoms physically cannot hold themselves together anymore.
Oh, wow.
Yeah, the electrons are literally ripped away from their nuclei.
So they just attach.
Exactly. So you aren't left with normal atoms anymore. You are left with this incredibly dense soup of free-roaming, negatively charged electrons and positively charged ions.
Okay, so the atoms themselves are completely dismantled. You just have all these loose electrical charges floating around in this chaotic soup.
Right. And because they are charged and because they're constantly moving around in this fluid state, they naturally generate electrical currents.
Oh, I see.
Yeah, it's one of the most fundamental laws of electromagnetism. Moving electrical charges inherently create magnetic fields. You just cannot separate the two.
Okay, so the movement creates the magnet.
Exactly. And because the entire mass of the sun is made of this flowing, electrically conductive plasma, the entire sun acts as a self-sustaining dynamo. The plasma's movement creates the magnetic field, and then the magnetic field, in turn, influences how the plasma moves.
That drastically changes how you picture it. It's like a living electrical fluid.
Yeah, that's a good way to look at it.
But the sun isn't just one big uniform blob of this plasma, right?
Yeah.
Like, it has a pretty deeply complex internal anatomy.
Oh, very complex, yeah.
Let's peel it back a bit. Let's start at the very center.
Okay, so at the very heart of it is the core. This is essentially the engine room where nuclear fusion takes place.
The nuclear engine.
Right. The pressure down there, just from the sheer weight of all the material above it, is crushing. And the temperature is around 15 million degrees Celsius.
15 million degrees. That's just, I can't even fathom that.
It's extreme. And under normal circumstances, two positively charged protons will naturally repel each other. It's much like pushing the north poles of two magnets together.
Right, they just slide apart. They don't want to touch.
Exactly. But the pressure and the heat in the solar core are so intense that they actually overcome this natural repulsion.
So they were basically forced together so violently that they fuse.
Yes. Through a process that heavily relies on quantum mechanics, specifically something called quantum tunneling, hydrogen protons smash together to form helium.
Okay.
And when they fuse, a tiny fraction of their mass is converted directly into pure energy.
And that releases light.
Right. It releases photons of light. And this is happening millions and millions of times a second, producing just an unimaginable amount of energy.
And all this light, it wants to escape, right? It wants to burst out of the core and radiate into space.
Naturally, yeah.
But right outside the core is this layer called the radiative zone. And the plasma here is incredibly dense, like so dense that a photon of light created in the core can't just travel in a straight line to get out.
Not even close. A photon will travel a tiny, tiny fraction of a millimeter before it crashes into an atom in the plasma.
Okay.
It gets absorbed by that atom, and then it is immediately re-emitted in a completely random direction.
Random. Like, it doesn't just keep going up.
No, it might go sideways, it might go backward towards the core, it might go slightly forward. And then it hits another atom, and the whole process repeats. Physicists actually call this the random walk.
The random walk. Hold on. I really want to make sure I'm grasping the scale of this.
Sure.
Because light is the fastest thing in the universe, right?
It is.
It takes what, like 8 minutes for light to travel all the way from the surface of the sun to the Earth?
Right, about 8 minutes.
But how long does it take for a single photon to navigate this random walk just through the radiative zone?
It can take upwards of 100,000 years for a single photon to bounce its way from the core to the outer boundary of the radiative zone.
100,000 years.
Yeah.
A photon is traveling at the literal speed of light. But this plasma is so thick, so dense, that it takes 100 millennia just to fight its way out of the sun's interior.
It's hard to wrap your head around.
It really is. I mean, that means the sunlight hitting our faces today, warming our skin right now, was actually created in the core before human beings even developed modern civilization.
Right.
Like Neanderthals were literally walking the earth when the sunlight you saw this morning was born.
It's a really profound realization when you think about it like that.
It's mind-blowing.
And, after that grueling 100,000-year journey, those photons finally hit a distinct boundary line deep inside the sun.
Okay, what is this boundary?
This boundary is called the tachocline.
The tachocline. Okay, I've heard this described before as like the velvet rope of the sun, separating the inner club from the outer club.
Right.
But that doesn't really explain what's physically happening to the plasma.
Yeah, a velvet rope is a bit too neat. A better way to visualize the tachocline is to think of it as the transition between a thick, stagnant, muddy swamp and a fast-flowing river.
Oh, I like that.
So in the radiative zone, the plasma is so dense it cannot physically circulate. The energy only moves outward because those photons are so slowly bouncing through it.
Right, the 100,000-year random walk.
Exactly. But once you cross the tachocline, you enter the outer layer, which is called the convective zone.
The river.
Yes, the river. In the convective zone, the density drops significantly. So the plasma is suddenly fluid enough to move around in bulk.
Okay.
This transition layer, the tachocline, is where the extreme shearing forces really begin. Below it, the inner sun is rigid and swampy. But above it, the outer sun is a churning, chaotic fluid.
Because the plasma in this convective zone is being heated from below, right?
Yeah.
By all those photons that are finally escaping the radiative zone.
Exactly.
So it creates this massive convection current.
Right. Think about a pot of water boiling violently on a stove.
Okay.
The water at the bottom, nearest the burner, gets incredibly hot. It becomes buoyant, and it rises rapidly to the surface.
Makes sense.
And when it hits the surface, it releases steam, or in the sun's case, it radiates heat and light out into space.
Right, which cools it down.
Exactly. Releasing that energy cools the plasma. And as it cools, it becomes denser and heavier again, so it sinks right back down to the bottom of the convective zone, hits the tachocline, and gets heated all over again.
Wow. So you basically just have to scale that boiling pot of water up until it's over 800,000 miles wide.
Pretty much.
And it's made of electrically charged plasma. So it's like millions of these massive convection cells, some of them the size of entire continents on Earth, just constantly bubbling up, cooling off, and sinking.
It is incredibly violent.
But convection is only one part of the chaos in this outer layer, right?
Right.
We established earlier that moving plasma generates magnetic fields. But to actually tangle those fields up, we need a second mechanical force.
We do. And that second force is called differential rotation.
Differential rotation.
Yeah. It answers the fundamental question of how a giant ball of fluid spins in space. You know, if you stand on the equator of the Earth, or if you stand near the North Pole in Greenland, you complete one full rotation every 24 hours.
Because the Earth is solid. We all spin together.
Exactly. The Earth is a solid sphere. It moves as a single cohesive unit.
But the sun isn't solid. You just explained that the inner core and the radiative zone, that dense swamp, they spin together like a solid ball. But the outer convective zone, the fast-moving river, does not.
Right. And helioseismologists, these are scientists who study the internal acoustic waves of the sun. They have mapped this out beautifully.
Oh, wow.
They discovered that the plasma at the sun's equator is basically racing. It completes a full rotation in about 25 days.
Okay, 25 days at the equator.
But as you move north or south toward the solar poles, the plasma becomes sluggish. Near the poles, it takes about 35 days to complete a single rotation.
Okay, let me make sure I'm picturing this correctly. You have this massive sphere of fluid, and the wide middle part, the equator, is constantly lapping the top and the bottom.
Yes.
It's continuously pulling ahead. So if this entire fluid is saturated with those invisible magnetic field lines we talk about, and the equator is spinning significantly faster than the poles, doesn't that inherently stretch the entire magnetic structure of the star?
It stretches it to the absolute breaking point.
Wow.
This is literally the heart of the solar dynamo. The magnetic field lines are what we call frozen into the highly conductive plasma. Where the plasma flows, the magnetic field is forced to follow.
He has no choice.
None. Astrophysicists break this massive mechanical stretching process down into two distinct phases. They call them the omega effect and the alpha effect.
The omega and the alpha. Sounds like something straight out of mythology, but it's just pure, terrifying fluid dynamics.
Yeah, pretty much.
So let's start with the omega effect. How does a faster spinning equator physically grab a magnetic field?
So imagine the sun during its most quiet, most relaxed phase.
All right.
During this time, its global magnetic field is actually remarkably simple. It looks like a classic bar magnet, what we call a magnetic dipole.
Right.
Picture invisible, perfectly straight vertical lines running straight from the North Pole down to the South Pole, just sitting there peacefully in the plasma.
But the plasma doesn't sit still.
Exactly.
The equator is racing ahead. So that fast-moving equatorial plasma physically grabs the middle of those straight vertical lines.
It grabs the middle and it drags it forward. The omega effect is driven entirely by that differential rotation we just talked about.
Oh, I see.
Over days and months and years, the equator just keeps spinning faster than the poles. It's constantly lapping them. So it takes those straight vertical magnetic field lines and pulls them horizontally.
Like stretching a rubber band.
Yes. It stretches them around the sun's waist over and over and over again.
So what started as a few really neat vertical lines running from north to south is now wrapped horizontally around the sun's equator dozens, maybe hundreds of times.
Right.
Like string being pulled really tight around a spool.
That's a perfect analogy.
The tension there must be astronomical.
It is.
But that is only half of the mechanical engine. The omega effect wraps the field horizontally. Where does the alpha effect come in?
The alpha effect is driven by the other massive force we discussed, convection.
The boiling water.
Exactly. That violent, boiling, bubbling motion of the plasma rising all the way from the Tachkline up to the surface.
Okay, so we have these tightly wound, horizontally stretched magnetic bands circling the sun under immense tension. And then billions of tons of superheated plasma come boiling up from underneath them.
Right. The rising plasma pushes against those tight horizontal magnetic bands. And because the sun is rotating, the rising plasma doesn't just go straight up, it twists.
Twists like a tornado?
Kind of, yeah. It's subject to the Coriolis force, much like how hurricanes on Earth begin to spin as they pull air inward. So this boiling plasma pushes the tight magnetic bands upward and twists them at the exact same time.
So you're pushing and twisting a band that is already stretched to its absolute limit.
Yes.
If you're listening to this and trying to picture what happens next, imagine you are holding a really thick, incredibly tense rubber band underwater.
Okay.
And you start twisting it in the middle. You twist it tighter and tighter. That's the alpha effect, working on the omega effect's tension. Eventually, that rubber band just can't take the structural stress anymore, right?
It has to give.
It buckles in on itself. It kinks up into this thick, knotted loop.
Yeah.
And what happens to a highly buoyant knot of air and tension underwater? It naturally rises.
It rises aggressively. Those twisted magnetic knots become highly buoyant and they rise through the convective zone until they physically punch right through the surface of the sun.
Wow.
And when those loops of tangled magnetic force break the surface, they finally become visible to us. We call them sunspots.
Sunspots. I mean, for centuries, astronomers looked through these rudimentary telescopes and just saw these dark blemishes appearing and disappearing on the sun's surface.
Yeah, Galileo drew pictures of them.
Right. But they aren't dirt, and they aren't shadows.
No, they are the physical scars of a magnetic knot exploding outward. And the reason they look dark provides a massive clue to their true nature.
Because they are physically colder than the rest of the sun, right?
Exactly.
But why would a magnetic knot popping through the surface make that area colder?
It's because the magnetic field inside a sunspot is incredibly concentrated. We are talking thousands of times stronger than the Earth's entire magnetic field.
Good Lord.
And this field is so intense that it acts as a physical dam. It blocks that normal convection process we talked about earlier.
The boiling.
Right. The hot, boiling plasma from deep inside the sun tries to rise to the surface, but the magnetic field of the sunspot pushes back and prevents it from reaching the top.
Oh, so it's a literal bottleneck.
Exactly. Because the fresh superheated plasma is blocked from coming up, that specific area of the surface just radiates its existing heat out into space and rapidly cools down.
How cool does it get?
It drops from about 6,000 degrees Celsius to roughly 4,000 degrees.
I mean, 4,000 degrees is still blindingly hot.
It is. It would shine brightly on its own for sure. But compared to the searing background of the rest of the sun at 6,000 degrees, the contrast makes it appear pitch black to our human eyes.
That makes sense. And these sunspots rarely just appear alone, do they?
Yeah.
I mean, the alpha effect is kinking these lines all over the place. We get these huge clusters of sunspots.
Yes, very rarely alone.
And when scientists look at these clusters in, say, ultraviolet light, the area above them isn't dark at all. It's violently bright.
Right. We call those active regions. In ultraviolet, you can actually see the glowing plasma tracing the immense arching loops of the magnetic field as it bursts out of one sunspot and plunges straight back down into another one nearby.
Like huge glowing rainbows of plasma.
Yes. And these active regions are essentially the powder kegs of the solar system. The magnetic field lines there are so deeply tangled and under such sheer mechanical stress that they are inherently unstable.
Which brings us to the breaking point. Because this constant winding and twisting and boiling and popping of the magnetic field can't just go on forever, right?
No, it can't.
A rubber band can only take so many knots before it completely snaps. And this entire process, the slow buildup of all this tension and the eventual violent release, it operates on a strict rhythm.
A roughly 11-year rhythm. It's called the Schwab cycle.
The Schwab cycle.
Yeah.
Let's trace the timeline of that heartbeat starting at the phase called solar minimum.
Okay.
We touched on this just a bit earlier. It's when the sun is in its most organized state. The magnetic field is a neat symmetrical dipole. It looks just like the Earth's magnetic field.
It does, but the clock immediately starts ticking. The equator starts outpacing the poles.
Right.
The omega effect starts stretching those vertical lines horizontally. By year 3 or 4 of the cycle, the alpha effect is violently pushing those horizontal lines up, creating hundreds of sunspots.
So the neat, clean dipole structure is completely shredded.
Absolutely shredded. The technical term scientists often use to describe the sun's magnetic field at the peak of the cycle, which we call solar maximum, is tangled up spaghetti.
Tangled up spaghetti.
It really is. There is no longer a clear north or south pole. It is just this overlapping, winding web of glowing magnetic loops snapping and twisting across the entire face of the star.
And it is within this tangled spaghetti that we actually see the most violent events in our solar system.
Oh, without a doubt.
Because when those twisted active regions finally reach their absolute limit, the magnetic field lines physically break.
Yes. The specific mechanism for this is called magnetic reconnection.
Magnetic reconnection.
Right. When these highly twisted, oppositely directed magnetic fields are shoved together by that boiling plasma, they can't simply pass through each other like ghosts.
Right. They have physical force.
They do.
Sure.
So they interact, they annihilate their current configuration, and they basically snap into a new, lower energy arrangement.
Kind of like the over-twisted rubber band finally snapping and instantly reforming into two smaller, more relaxed loops.
That's a great way to picture it.
But that snap has to release all the stored up tension all at once, right?
And the energy released by just a single magnetic reconnection event is staggering. It produces what we call a solar flare.
Which is?
It's an intense flash of pure electromagnetic radiation light, X-rays, gamma rays. A massive flare can release the energy equivalent of millions of nuclear bombs detonating simultaneously.
Millions of nuclear bombs.
From one snap.
From one snap, and a flare is basically a flash of light, so it hits the Earth in 8 minutes.
Right.
But during solar maximum, these snapping magnetic fields can also trigger something far more dangerous, right? Something called a coronal mass ejection, or a CME.
Yes. A solar flare is just a flash of light, but a coronal mass ejection is a physical eruption of matter.
Oh, okay.
When the magnetic structure over a sunspot catastrophically fails and reconnects, the sheer explosive force of it can completely sever a huge portion of the sun's outer atmosphere.
Just blows it off.
It literally rips away billions of tons of superheated plasma, along with the magnetic field embedded inside of it, and hurls it out into the vacuum of space at millions of miles per hour.
I want you to sit with how surreal that is. Like, as you go about your day, you're getting coffee, you're answering emails, there is this monstrous ball of liquid plasma in the sky that is mechanically winding itself into a chaotic knot.
Yeah.
And it hurls billions of tons of radioactive shrapnel out into the void. Our entire solar system is subjected to an 11-year season of sheer magnetic violence. We basically orbit a ticking clock.
We do. But the clock does eventually reset. The sun doesn't just stay a tangled ball of spaghetti forever.
Well, that's a relief.
To escape solar maximum and return to the neat, calm dipole of the next solar minimum, the sun has to undergo a process so massive it almost defies logic.
Okay, what does it do?
It undergoes a complete global magnetic flip.
The great flip. So we said that at solar minimum, the sun's magnetic north pole is at the geographic top and the south pole is at the bottom.
Right.
But as the omega and alpha effects tangle the field up, those global poles start to lose their anchor.
They really do. The immense distortion from all that differential rotation causes the global magnetic poles to physically migrate.
Migrate. Like they move down.
Yeah. Over the years approaching solar maximum, the magnetic North Pole slowly tilts away from the top of the sun, wandering further and further down the latitudes until it is pointing roughly at the sun's equator.
That is geographically insane.
Yeah.
Imagine if Earth's magnetic North Pole just started wandering from the Arctic, down through Canada, straight through the United States, until our compasses all pointed toward Ecuador.
It would be pure chaos. And on the sun, it continues to devolve even further.
How does it get worse than pointing at the equator?
Well, by the time the sun hits absolute solar maximum, the localized magnetic chaos from all the hundreds of sunspots is so incredibly intense that it actually drowns out the global magnetic field completely.
Wait, really?
Yeah. The main poles become completely undefined. The sun is essentially suffering a massive geographical identity crisis. There is no clear up or down magnetically speaking.
It's just a localized mess of compass-breaking storms everywhere.
Exactly. But then slowly, as the magnetic reconnection events snap and release all that built-up tension, the field begins to relax.
Okay.
The overarching magnetic structure slowly reorganizes itself into a simpler state. The sun begins to calm down, approaching the next solar minimum. The poles reappear, and they actually finish their migration, moving back to the top and bottom of the star.
But when they finally lock back into their vertical positions, they are upside down.
They are completely upside down. The magnetic pole that spent the previous cycle pointing at the geographic top of the sun now points to the very bottom.
Wow.
And the pole from the bottom is now at the top. The entire magnetic polarity of the star has fully inverted.
A celestial body roughly 1 million miles wide, holding like 99.8% of all the mass in the entire solar system, physically flipping its magnetic north and south poles every 11 years.
It's incredible.
I mean, Earth's magnetic poles have flipped in the geological past, sure, but it takes hundreds of thousands of years for the instability to build up here, and thousands of years just to complete the actual transition.
Right.
The sun executes a total polarity reversal on a timeline you can track just by watching a child go from kindergarten to high school.
It's a wildly fast timeline for something of that scale. And because a single 11-year Schwab cycle leaves the sun magnetically upside down, it actually takes 2 full cycles, roughly 22 years, for a complete magnetic journey to finish.
To get back to normal.
Right. We call that 22-year period the Hale cycle, which is the time it takes for the poles to flip again, and return to their original starting orientation.
Okay, so we've traced this entire internal engine. We watched the 100,000-year swamp of the radiative zone give way to the fast-flowing river of the convective zone.
Yep.
We saw how the differential rotation, the fast-spinning equator and the sluggish poles, pulled the invisible magnetic fields horizontally around the sun's waist in the omega effect.
And then the alpha effect.
Right, the boiling, twisting plasma of the alpha effect, kinking those stretched lines, forcing them to buckle and burst through the surface as those highly concentrated dark sunspots.
Exactly.
We watched the neat, symmetrical dipole of solar minimum completely devolve into a terrifying web of tangled spaghetti at maximum, unleashing millions of nuclear bombs worth of energy in flares and hurling billion-ton clouds of plasma as CMEs.
And the poles flipping.
Right. The complete loss of geographic identity, migrating until they reform upside down. But here is where we really bring it all home, because this chaotic 11-year heartbeat does not stay neatly contained on the surface of the sun.
It definitely does not. Space is not empty.
Right.
When a coronal mass ejection, that billion-ton cloud of tangled magnetic plasma, is hurled away from the sun, it actually expands as it travels through space.
Like a shotgun blast.
Kind of, yeah. And if Earth happens to be in the orbital crosshairs of that huge eruption, we experience the full force of space weather.
So we started this whole conversation talking about the Carrington event in 1859, right? Where telegraph operators were literally getting electrocuted by their own machines.
Yes.
How does a cloud of plasma from the sun physically set a piece of paper on fire down here on Earth?
It all comes down to how magnetic fields interact with each other. The Earth has its own magnetic field, right? Our magnetosphere, which acts as our protective shield.
Right, our deflector shield.
Exactly. When a massive CME hits Earth, its intense magnetic field violently slams into our magnetosphere. The collision dramatically compresses Earth's magnetic shield on the day side and stretches it out like a tail on the night side.
Okay, so the shield is bending under the pressure.
Yes. And this rapid, violent compression and stretching injects a massive amount of kinetic energy and all these charged particles directly into our upper atmosphere.
Visually, this is what gives us the auroras, right? The northern and southern lights.
Yes, that's exactly what that is.
Because the solar particles get funneled down the magnetic lines right at our poles. And when they slam into oxygen and nitrogen molecules in our atmosphere, they basically excite them, causing them to glow like giant cosmic neon signs.
Auroras are absolutely stunning to look at, but the invisible mechanical effect of that shifting magnetic field is far more dangerous.
Why is that?
Well, according to Faraday's law of induction, a rapidly changing magnetic field will induce an electrical current in any long conductor it passes over.
Oh, any long conductor.
Right. So during the Carrington event, the massive magnetic storm induced huge electrical currents into the longest conductors available at the time. The thousands of miles of telegraph wires strung across the globe.
The sun literally used our telegraph network as an electrical coil. generating power out of thin air until the wires overheated and caught fire.
That's exactly what happened. Now, consider what a solar storm of that exact same magnitude would do today.
Oh, wow.
We have spent the last century wrapping our planet in a fragile, incredibly complex web of high-voltage transmission lines, oil pipelines, and fiber optic cables.
Right.
A severe geomagnetic storm today could induce massive direct currents straight into our power grids, destroying these massive custom-built transformers that take months, sometimes years to replace.
Not to mention all the infrastructure we have sitting up in space now.
Oh, absolutely.
When the atmosphere absorbs all that solar energy, it heats up and expands outward, right?
It does.
So low Earth orbit satellites suddenly find themselves flying through thicker atmospheric drag than they were ever engineered for. They lose altitude, they can burn up in the atmosphere.
Yeah, we've lost Starlink satellites to this very phenomenon.
And GPS signals just get totally scrambled by all the dense ionization. I mean, it is a really stark reminder that the sun's cycle is a direct, ongoing operational hazard to our entire modern way of life.
It really forces us to respect the environment we actually live in, but, it also profoundly changes how we view the rest of the galaxy.
Yeah, so?
Because our sun is completely ordinary.
Right.
There are billions of stars just in the Milky Way alone, and they all operate on the exact same principles of plasma dynamics, convection, and differential rotation.
So other stars have their own alpha and omega effects.
They do.
They have their own sunspots, their own tangled spaghetti phases, their own solar flares, and their own massive coronal mass ejections.
We can actively observe this. Depending on the mass of the star and how fast it rotates, its magnetic cycle might be a few months or it might be several decades. But the basic engine is universal.
Which, if you think about it, completely upends how we think about the search for extraterrestrial life.
Oh, 100%.
Because usually the conversation just begins and ends with the Goldilocks zone.
Habitable zone. Right. For decades, the primary metric for whether an exoplanet could harbor life was purely based on orbital distance.
Right. Is the planet far enough from its star that the water won't boil away, but close enough that it won't just freeze solid?
Exactly. If a planet had liquid water, it was considered a prime candidate for life.
But if we apply everything we just unpacked today about the internal magnetic engine of a star, that orbital distance feels almost irrelevant.
It certainly complicates things.
Like if you have a planet sitting perfectly in the Goldilocks zone with beautiful oceans and a nice thick atmosphere, but its host star is a magnetically chaotic monster, that planet is an extreme danger.
You've hit on probably the most critical paradigm shift in modern astrobiology right now.
Yeah.
We're realizing that a star has a deeply dual nature.
Okay.
Yes, a star's light and heat are absolute prerequisites for life as we know it. It drives the climate, it allows for complex chemistry, but the star's magnetic cycle acts as a cosmic blowtorch.
A cosmic blowtorch. Take a system like TRAPPIST-1. That one made massive headlines because it has multiple Earth-sized planets sitting right in the habitable zone.
Right.
The TRAPPIST-1 is a red dwarf star. It is incredibly active magnetically.
And because it is a smaller, cooler star, its habitable zone is physically much closer to the star itself. Those planets are orbiting very tightly.
Oh, so they're right in the line of fire.
Exactly. If a star like TRAPPIST-1 is constantly undergoing massive magnetic reconnection events, constantly hurling powerful stellar flares and violent coronal mass ejections outward, those planets are taking a severe continuous beating.
So if the planet doesn't have a planetary magnetic shield as strong as Earth's to deflect that incoming plasma, what actually happens to it?
The relentless barrage of high-energy particles from all those stellar CMEs will physically collide with the molecules in the planet's upper atmosphere.
Okay.
The stellar plasma imparts so much kinetic energy to the atmospheric gases that they literally reach escape velocity.
You just float away.
They get blasted away. Over the course of millions of years, the host star's magnetic temper tantrums will completely strip the protective atmospheric envelope away, bleeding it entirely into space.
It sandblasts the atmosphere right off the planet.
That is a very accurate way to describe it.
And once the atmospheric pressure drops, the liquid water on the surface just boils away and is lost to space as well,
leaving behind a completely barren, irradiated rock, forever sterilized. It makes the equation for finding alien life infinitely more complex. We cannot just look for a planet at the right distance anymore. We have to find a planetary system that has successfully survived the sheer magnetic chaos of its own host star.
It's just staggering. So let's wrap our heads around the absolute scale of the journey we've taken today. We started at a solid core of immense crushing pressure, where quantum tunneling forces hydrogen to fuse into helium.
Yeah.
We watched the resulting photons endure a 100,000-year random walk, bouncing endlessly through the dense swamp of the radiative zone.
We crossed the Tashikline, entering that boiling fluid river of the convective zone.
We saw how the differential rotation, the fast-spinning equator, and the sluggish poles pulled the invisible magnetic fields horizontally around the sun's waist in the Omega effect.
And we watched the boiling, twisting plasma of the alpha effect kink those stretched lines, forcing them to buckle and burst through the surface as highly concentrated dark sunspots.
We watched the neat, symmetrical dipole of solar minimum devolve into a chaotic, terrifying web of tangled spaghetti at solar maximum.
The peak of the chaos.
We saw those immensely stressed magnetic lines snap and reconnect, unleashing millions of nuclear bombs worth of energy in solar flares, and hurling billion-ton clouds of plasma across the solar system as coronal mass ejections.
And we witnessed a 1,000,000-mile-wide star completely lose its geographic identity.
Right. Migrating its global poles through a mess of magnetic storms until they reformed utterly upside down.
And finally, we tracked the shrapnel of that engine across the vacuum of space, watching it compress our magnetosphere, light up our skies with auroras, threaten our fragile technological grid, and rewrite the rules for where life can even attempt to exist in the broader galaxy.
It is an absolutely breathtaking, horrifying, and beautiful mechanism. I want to leave you with a final thought to ponder as you go about the rest of your day. We started by asking you to just look up at that calm, yellow disk in the sky. Think about the profound cosmic paradox of what that disk truly is. A star is the ultimate giver of life. Its warmth and its ancient light are the only reasons we breathe, the reason plants grow, the reason liquid water flows on this planet, yet its internal magnetic clock, its inevitable, unavoidable cycle of winding tension and tangled chaos, makes it the ultimate destroyer.
It really does.
It is a cosmic blowtorch, fully capable of violently stripping the very air away from the worlds that orbit it.
So when you look up at the sun today, shielding your eyes from the glare, ask yourself, how miraculous is it that our tiny Earth, armed with nothing but its own invisible, delicate magnetic shield, has somehow managed to survive billions of years, thriving right next door to this twisting, erupting magnetic time bomb?